Here we're asked to draw the molecular orbital energy diagram to determine the bond order in a molecule or ion that has 10 valence electrons. So we're dealing with these s and p orbitals, the pi's and sigmas, both the bonding region, the bonding molecular orbitals, and the anti-bonding. So if we remember that the definition, the formula that we'll be using for the bond order, it'll be 1/2 times the number of electrons that are in the bonding regions or the bonding MOs minus the number of electrons in the anti-bonding MOs. I'm a little, I like going with shorthand a little bit. So the way that I actually write down this is bonding MOs is BN MOS minus antibonding, which is just A BN MOS. Just because I like to try to be efficient with how I write everything out. But it always will be the number of electrons that are considered to be bonding versus antibonding. So you have to remember that there's a split between the sigma and the sigma antibonding, and then the pi's and the pi antibonding. The bonding orbitals will always be less energy than the original atomic orbitals, and the antibonding will always be higher in energy than both. So something like this, oh, that's really a bad straight line. Something like this should start to look a little familiar, where you have one energy level for, say, a 2s orbital, and you're going to start out with what you would originally have for 2s, but you're going to have an elevated, you have an elevated and then a decreased energy level, which I don't know why I'm going dyslexic all of a sudden. I should be dotted line. There you go. And this is going to tell us what our bonding and our anti-bonding sigmas are. Now, what's really nice about this, I was told that I have 10 valence electrons, which means I know I'm not in the first row, which would only use one s. So 10 valence electrons, I'm looking at n equals 2, which is both s orbital and p orbital. So I can go ahead and use my two 2s orbitals that I would have for my valence electrons and make my bonding and anti-bonding sigmas from those. So I always start with Hund's rule. You always go with the lowest energy level first, one electron up, then down. So the bottom bonding sigma is filled. Next up is the anti-bonding, up and down. Now, if I was to stop here, just looking at the filled sigmas from my 2s's, my bonding order here would be 2 bonding molecular orbital electrons minus 2 anti-bonding molecular orbital electrons divided by 2, which is simply 0 over 2, which is 0. So if you have more than 4 valence electrons, the first 4 will always result in a bond order of 0 because they're going to cancel each other out from the 2s's that are going to be utilized. Now we're going to look at the 2 p's. So you remember if you with the p orbitals, you have 3 different sets. You can have the p sub x, the p sub y, and the p sub z. So I'm going to have my 2 p's set up here. Now this is where I have the multiple splitting here. I can have my pi bonds above my sigma or below. It all depends on what my molecule is. Like if it's carbon, it'll exhibit high sp mixing. If it's oxygen, it'll be low. But since we're just dealing with the number of valence electrons, we don't really have to worry about whether or not it'll be sigma first, then pi, because all we really care about is the bond ordering. So all we really care about is how many electrons are going to be in the bonding molecular orbitals and which ones are going to be anti-bonding. So I'm going to start with sigma, and then I'll start with, and above that will be my 2 pi's. And then I have my regular line, my energy level for my p orbitals. Then above that will be my 2 anti-bonding pi orbitals. And then above that will be my anti-bonding sigma. However, I had just used 4 electrons in my 2 2s orbitals, which means I only have 6 electrons to work with my p's. So that means I'm going to have 3 from the first on one side and 3 on the other. So those are where my original electrons were. Now we start from the lower energy level and we fill up using Hund's rule. So the lowest here is going to be sigma, so we're going to do our up and then our down first. 2 down, 4 to go. We fill up our up spins and our the pi orbitals first, and then our down spins. And that's 4, which means I've used up all of my electrons. So now let's look at the bond order based on these 2p atomic orbitals, the way that we separated them out into our molecular orbitals, my bond order here will be 1, 2, 3, 4, 5, 6 bonding electrons minus 0 anti-bonding electrons. Divide that by 2, which is just 6 minus 0 over 2, which is simply 3. So my overall bond order is a positive 3. Now, what's really nice about this is for 2s and 2p, the way that we have this situated, the highest bond order that you can have is a positive 3. After that, if you start putting in more electrons, your bond order will start to decrease because you're going to start to increase the number of anti-bonding molecular orbital electrons. And if you have a valence number that's greater than 4, you can go ahead and subtract 4 from the number of electrons that are even going to be meaningful in the bond order, because the first 4 are going to cancel out based on the 2s atomic orbitals that you worked with. So the one thing to keep in mind is just remembering how you're situating your energy diagram. The bonding orbitals will go below the atomic orbitals. The anti-bonding will go above the atomic orbitals.